Welcome to Worst Case Analysis using Mathematica. This is an introduction, and it's brought to you by Right Paradigm Consulting. I'm Jay Oplinger, the author. Now, we want to use Mathematica to do worst case analysis because it allows us to work through the mathematics of the problem and make sure we have the solution, and then we can go back and we can document it using the word processing capabilities of Mathematica. Now, if you've never used Mathematica, go to this hyperlink here and click on it, and it will take you to Wolfram's Introduction to Mathematica video, where you can get a feel for the types of things Mathematica does and how it does them. The first thing we're going to look at is lists and matrix formation. A list is a group of variables and numbers separated by commas inside of curly brackets. For example, a list is the function we're going to call, or the variable we're going to call this, and it's 1, a, 2, b. And if we execute that by highlighting the right side and hitting Shift Enter, notice it shows you what the a list is defined as. Now, if you do not want to see the output, then you put a semicolon after something like B list, and if we hit Shift Enter, notice it doesn't repeat back what we defined things were as. Now, if we can use lists to make matrices. In this case, we're going to call a matrix a list, b list. So we will enter that. And now we're going to use the directive matrix form so we can look at this matrix as you would if you wrote it down yourself on a piece of paper. Notice it has the two lists, and they puts them together as a row matrix. Now you can create a matrix of all columns, and if you can do that by putting both lists enclosed in curly brackets. And then we go B list or B matrix, and then look at that in a matrix form, and notice there are two columns. So the third way we can put these together in a matrix is we can create a matrix of two columns. And the way we do this is by putting the curly brackets surrounding the A list, B list. And now we'll show you what that looks like using matrix form. So we have two column matrices, or two column matrix. Now, once we have a matrix, it's always fundamental to be able to pull out pieces of it that we want to look at. And so the way you do that is you use the variable name, put two square brackets, and then put the element you're looking for. So for example, if we want to get the first row of the A matrix, we would use this terminology of square bracket 1, and then we've pulled out the first row of the A matrix. If we want the third element of the first row, then we would put it as 1, 3, and that would give us the third element, which is a 2. So using this approach, we can get any element in any matrix. And that will be very helpful when we start doing worst case analysis. Now, replacement rules. The final operation, when we've done the worst case analysis, we usually end up creating an equation, and we want to maintain that equation as an algebraic expression, but we want to substitute values into it. So here I've made up a simple equation. We call it equation A. It's x squared plus x. So we will enter that into Mathematica, and now we want to evaluate that at x equals 2. So we do that by writing out the value, then a backslash period, and then what we're going to replace in the equation. In this case, there's only one variable, x. So we're going to put in x is replaced with 2, where the arrow is like the replacement operator. Now, if we do that, we get 6. And if you look at it, 2 squared is 4, plus 2 is 6. So the beauty of this is the equation remains as an algebraic equation. So we don't lose that ability. Now, we want to create lists sometimes using a table function. And a table function is just a way of creating a list. So here we want to create a table of equation A for x varying between 1 and 9. Now, if there's no third argument, then it's assumed that the table increments by 1. If you want a different increment, you can put a comma in there and say 0.5, and then it would increment by a half. So let's create this table. We'll call it val A. And notice it computed 1, 2, 3, what equation A is for all those different variables. Now, normally in mathematics, we're more interested in ordered pairs. We want an independent variable and the result of the dependent variable. So let's actually change the value of A, of val A, by creating a table, and each element is going to be the x and the equation A value. So if we do that, and notice we put a semicolon here because we don't want to see the results, and now we'll look at that in matrix form, and we have a set of ordered pairs. Now, most people respond much better to looking at plots of functions instead of just looking at the equations or the numbers, because you can see a lot more information from that. To do that, we're going to use this list plot function, and we're going to look at what that val A would look like if we plotted it. So here is the dots that represent the 1, 2, up to 9, and their y values. Now, a lot of times it's much more helpful if we add labels to these graphs so that we can tell people this is what this variable is and this is what the other variable is. So notice we're going to have input values of x and output values of y. And there are the labels. Now, we might want to connect the dots. So if we want to connect the dots, we use list line plot instead of just list plot. And then we can create an output that looks somewhat like a curve, even though these are all straight lines. Now, tolerances. Once we have a circuit, each one of the components in the circuit has a tolerance. So just to look at this simple-mindedly, let's say we have a 1 k ohm resistor with a tolerance of plus or minus 1%. We could write that out as, say, R23 is 1,000 times 1 minus 0.01, comma 1 plus 0.01. So this is going to multiply through, and in essence we're going to create a short list, a 2-element list of the 2 different values, extreme values of that particular resistor, 990 and 1010. Now, since this has 2 values associated with it, if we, for example, put it into the equation A that we've used before, we'll get 2 answers out. We'll get one that represents the minimum and one that represents the maximum. And indeed we do get that out. So that's how we're going to enter the tolerances for components when we do worst case analysis. Now, in review, this file in Mathematica is known as a notebook. In future notebooks, we're going to explore the basic steps in creating worst case analysis and how to format the equations, determine min, max values, and convey the results for a reviewer. This notebook introduced you to how to create a matrix, extract parts of a matrix, and replace variables, and create upper and lower limits. Now, the next time, we're going to look at how circuit analysis is normally performed. We'll explore the mathematical format we will use and an author-created function that will really do a lot of the heavy lifting for you in terms of organizing the equations, setting them up in a matrix, and then from there we'll be able to use Mathematica's functionality and problem-solving ability to get the answer. We look forward to talking with you again in the next video.